but the recent several years, we moved to the transition metal compounds such as YBCO on the lutetium ferrite and the alpha spin-reacted alpha ruthenium trichloride, and also the VO3. And to consider about that, we have to think about the energy, or equivalently the time scale for the material parameters such as the Coulomb repulsion and the intersite charge hopping and the elementary excitations. Just after the excitation by light, which is the oscillating electromagnetic field with the period of several femtoseconds in the case of the near-infrared light. After the radiation, we need at least several picoseconds or several tenths picoseconds to realize the change, macroscopic change of the symmetry. However, to understand the microscopic nature of this macroscopic symmetry breaking, we need to capture these time scale from 100 a second to several tenths femtosecond. That is a key point for my talk. To capture these time scale, we have developed the several femtosecond carrier envelope phase several femtosecond light source. And now we continue to develop shorter paths toward the one watt. We have memory effect. Sorry. 1 watt 2 femtosecond by using the technique of the light synthesization. Okay, let me introduce our collaborators. The ultrafast experiment have actually done by our these guides in our research group. And as for the YBCO and the VO3, we collaborate with many persons. In particular, for VO3, I will mention about the collaborator in the later section. Okay, let's start the first topics. There is a generation dynamics of the quasar particle in high temperature superconducting cuprate. There are many studies on the recovery relaxation dynamics of the superconducting quasar particles on time scale or picosecond, in particular focusing on the low energy dynamics by using technique of TDS or the transient RFS. However, the generation dynamics of quasar particles is still puzzling because of its ultrafast within 100 femtoseconds and very complicated nature. To clarify this problem here, we focused on the spectral rate transfer in the very wide spectral range between 0.1 to 4 electron volt to characterize how fast the generation of a quasar particle occurs. And we also investigated building up dynamics of the coherent, low frequency coherent phonon to consider the mechanism of the quasar particle generation dynamics. The spectral rate transfer upon the superconducting phase transition is known to give a spectral rate transfer, but in conventional superconductors such as this system is very occurs in very limited times, limited energy scale of milli-electron volt. And that is very different from the unconventional superconductivity, such as in cuprate, where the spectral rate transfer occurs in electron volt or several electron volt. There is a characteristic feature sometimes detected in the strongly correlated system. Actually, almost 10 years ago, right in the spectral weight increase around the near-infrared light range have been reported in Bismuth 2212 system, right here. And they have discussed in terms of the spectral rate transfer from the low energy Druid component or the mid-to-infrared absorption component to the near-infrared region. However, there are no experimental confirmation. So we should expand the spectral range from the high energy range. And we can characterize how fast the spectral rate transfer or equivalently the generation of the quasi-particle occurs. That is the first purpose. The second thing is the coherent phonon. The 3.5 terahertz and 4.5 terahertz mode coherent phonons are very famous, which are attributed to the BA and CU atomic motion along the C-axis. Although the superconducting electric properties on the CO2 plane, the observation by the right polarization parallel to the AB plane comes from the buckling structure of the CO2 plane and the electron phonon coupling. Actually, the right Pump-Probe experiment detected in the AB plane can clarify the clear observation of such oscillating structure. And it is noteworthy that the amplitude of the BA mode showed clear increase below the superconducting field transition temperature, although that for the CU mode is not so clear. This result easily reminds us the specific excitation mechanism. However, the high time resolution measurement is not consistent with this specific excitation mechanism. There is still puzzling problem. Although the 4.5 terahertz mode has been assigned to the DCP mechanism. After that, this 4.5 terahertz CU mode has been assigned to the local CU mode. Okay, so our first purpose is to measure the spectral rate transfer from where to where, and how fast it does occur, to discuss the time scale of the generation of the superconducting quasi-particle. And the second thing is that by measuring the build-up dynamics of the coherent phonon to discuss about the origin of the spectral rate transfer. Okay, first result is the transient reflectivity measured by conventional using the conventional 100 frames per second light pulses. This figure shows the transient reflectivity between 0.1 2 eV to 4 eV as a function of time delay up to 10 picosecond. And the pumping energy is around here, and the red and the blue area respectively shows the transient reflectivity increase and decrease. And in earlier studies, these areas have been already reported, but the other area has not been detected. So this is the first report for this spectral area. And this transient reflectivity is very different from that observed in the normal state. So this behavior is very characteristic to the superconducting phase. Okay, if we focusing on the first 1 picosecond, we can notice very complicated nature. If we cut the spectral profile at time zero, around time zero, we have a very clear peak around the plasma edge in the steady state reflectivity, together with the very broad reflectivity decrease. And it is very important to suppress the pumping intensity. If we use the higher intensity, the spectral shape become very, very different. Anyway, it is very important that during the first 300 femtosecond, spectral shape around here showed very drastic change from the negative to positive, as shown here. And we can expand the figure. The spectral shape showed very, very drastic change from here to here. We will be able to discuss about the origin of this spectral change during the first 200 or 300 femtosecond. Okay, we would like to discuss this transient reflectivity. We use the analysis, phenomenological analysis using the Drude-Lorentz analysis, which has been used for analyze the steady state, the reflectivity or the conductivity spectrum, optical conductivity spectrum. And although around here, the detailed physical assignment is still controversial, but here we just phenomenologically use this method. Basically, the spectrum is consisting of the Drude component, mid-infrared component, interband, so-called interband, and several interband transitions. And the result of the analysis is shown here. We have successfully reproduced the shape of the transient reflectivity spectrum. Here we assume the increase of scattering rate as well as the change of increase or decrease of the spectral rate or respective band. And the result is that the spectral rate transfer occurs from the interband transition at 1.9 and 2.9 electron volt to the interband 1.5 eV and 0.1 mid-infrared absorption. In this time range, it looks like the negative component. As I thought, it changed to positive within the first 300 femtoseconds. So totally, I can say that the spectral rate transfer occurs from the low energy to high energy state. And it is noteworthy that also the Drude component is a little bit increased in this analysis. And it is noteworthy that this spectral rate transfer is very different from the result for the normal state, where the spectral rate at the both sides, both lower energy and higher energy side, transfer to the intermediate 1.5 or 2 electron volt range. So they are very different things. I'm not sure what is the origin of this difference, but anyway, they are very different. So our purpose is to determine the time scale for such kind of the spectral rate transfer. The red dot shows the spectral rate, scattering rate, increase of scattering rate, which increase immediately after the Fourier excitation. On the other hand, for the spectral rate increase for the interband and the mid-infrared band shows the very short build-up time of about 100 femtoseconds. But you know, it is difficult to discuss about such 100 femtosecond time scale by using the 100 femtosecond pulses. So we move to the result of the 6 femtosecond light pulses. Okay, this is a result. Time evolution of the reflectivity. We have a negative and positive component. According to the spectral analysis obtained by using the 100 femtosecond result. These negative and positive component attributed to the increase of the scattering rate of the mid-infrared absorption, and the spectral rate increase for the mid-infrared absorption and the interband transition. Okay, so and we can show you the spectral reserved analysis. Okay, here is the we can use the very broadband spectrum of 6 femtosecond light pulses, and this spectral range corresponds to here, and we can follow the spectral change from here to here, and determine the time scale of the increase of spectral rate is 70 femtoseconds. So there is a time scale of the spectral rate transfer induced by the light radiation. The next thing is that the build-up dynamics of the coherent phonon. As I told you, we have two low-frequency coherent phonon at 3.5 terahertz and 4.5 terahertz at the BA and CU mode. And by subtracting the background component, we can obtain the oscillating component. We can confirm the 3.5 and 4.5 terahertz coherent phonon, and also confirm the cosine-like and the sinusoidal initial phase. In addition to that, we also have the optical oxygen high-frequency coherent phonon. That has been already detected in room temperature, but that is the first observation at the low temperature phase. But here, we would like to discuss only about these coherent phonon. This is the wavelet result of wavelet analysis. As a function of the Pamplov time delay, the frequency changed. But be careful for the time range is very short in comparison with that for the time scale of the period of the coherent phonon. So it's not so simple. And within the period of the coherent phonon, we cannot distinguish the difference of 4.5 and 3.5 terahertz mode. Actually, we have a peak in the intermediate range. And as for the 4.5 terahertz mode, it showed the monotonic decrease as a function of time. However, the 4.5 terahertz mode showed very complicated nature. First thing is that it looks like the building up on the time scale of about 100 femtoseconds, and the frequency showed some modulation. And not yet we have not reached any conclusion about the reason for such the modulation. But anyway, such build-up time of 100 femtoseconds and the frequency modulation cannot be explained by the simple the ISR's mechanism. So we have two possibilities. The one possibility is of mode-mode coupling between the 4.5 terahertz and the 3.5 terahertz mode. 4.5 terahertz mode can be driven by the DCP mechanism. And if we have the coupling between them, between the 4.5 terahertz and 3.0 terahertz mode, the 3.0 terahertz mode can be driven the other sinusoidal, the initial phase coherent phonon. There is one scenario. The another one is the more complicated. In the DCP model, according to this theoretical paper, described by the group of Tragman at 2012. The initial phase is very sensitive to the coupling strengths of the electron phonon. If this is possible, applicable for this situation, that is possible to explain the initial phase of this coherent phonon, but I'm not sure. So the finally of this session of this part is to consider about the relation between the build-up time of the coherent phonon, low frequency coherent phonon, and the build-up time of the spectral rate transfer. Let me remind you that the build-up of the spectral rate transfer is about 70 frames per second. The time scale of which is almost equal to the write-up of this 3.5 terahertz mode. So we strongly suggest the relation between them. We can say the build-up of the spectral rate transfer is driven by the low frequency coherent phonon with the frequency of 3.5 terahertz mode, or the build-up of the coherent phonon is driven by the spectral rate transfer. There is a second conclusion. Okay, the summary for the superconducting YBCO, we have observed the spectral rate, right-induced spectral rate transfer that is very characteristic to the superconducting phase. And the spectral rate transfer occurs high energy to lower energy. And the characteristic time scale of that is about 70 frames per second. And this time scale is almost agree with the building up time of the 3.5 terahertz coherent phonon. So we suggest the relation between them. Okay. Okay. More about 10 or 12 minutes. Okay, okay. So the next part, totally the 40 minutes with the question.
You have more than 10 minutes. You have
Okay, okay. So the 15 minutes, including the question. Okay, okay. So the second part is given for the V03. I guess the next week, the Etienne has already give a talk about that, but I'm afraid everyone has forgotten the contents. So after the brief summary, I will give new topics. The collaborators, this work has been done by the big collaboration with these guys. In particular, for the X-ray experiment, the Nanto and Ren group has read the experiment. Okay, the V03 is very famous material as a textbook modulator, but not so simple. In the phase diagram, the bandwidth control Motton transition, we are here for the pristine V03. And the phase transition around the 150K, the insulator to metal transition with the symmetry change from the monoclinic to the quantum phase. Here, in the AFI phase, this kind of the shear distortion occurred to stabilize the antiferromagnetic electronic state. And the structural change involves both the symmetry change and the volume change. Volume change. In our opinion, such material is very suitable for considering the cooperative working between the electronic, the electron correlation and the electron phonon interaction. There are several studies on this material. of course, for the light irradiation. But they have discussed in terms of the nucleation growth by the laser heating. Actually, they irradiate light just below the phase transition temperature, such as the 100 K. But according to the very simple heat evaluation, the necessary required heat for realizing thermally induced insulator metal transition is the meaningful larger than that for the required work for the pressure induced insulator metal transition. So the light-induced pressure-driven insulator metal transition is more likely to occur. That is our motivation. To demonstrate this problem, the motivation is that. First thing is that suppress the temperature at very low to avoid the laser heating, reaching to TC, such as 10 K. And we have to detect both the electronic state, such as the clothing gap by the reflectivity and the structural change in the enough time resolution. And to avoid the kind of the I forgot the name of cramping effect. To avoid some cramping effect detected in the bulk sample, we use the nanocrystalline sample. I skipped the detail, but this nanocrystalline sample, nanocrystalline thin film with a thickness of 100 nanometer, 200 nanometer, 70 nanometer, 270 nanometer, and the diameter of this is about 20 nanometer. It showed very good electronic nature, which is almost similar to the bulk crystal for the phase transition, insulator to metal transition. And here, this is a optical constant for the bulk crystal. And the experimental condition is shown here. The pumping energy is just above the gap. And the probing area is cover the closing of the gap for the 100 femtosecond and 6 femtosecond, right, pulses. Okay, the transient reflectivity shows the under the excitation of several millijoule pascal centimeter, very big intensity, the 100% change of the insulator to metal transition occurs. The transient reflectivity spectrum completely the same as the temperature difference spectrum. Okay, that is the first things. And we also have the very clear signature of the macroscopic phase transition. We have this is the efficiency of the phase transition as a function of excitation intensity. We have a very clear threshold-like behavior at 2 millijoule pascal centimeter. There is a fingerprint of the macroscopic phase transition. And in the transient reflectivity spectrum, we measure both the volume change and the symmetry change. They are the indication for the insulator to metal transition in this material. And interestingly, the time scale of them very striking. The symmetry change from the monoclinic to quantum phase occurs in few picoseconds. And there is much faster than that for the volume change. There are the 16 picosecond, 40 picosecond, which are very sensitive to the film thickness and can be explained by the propagation inside of the thin film by the longitudinal acoustic wave. And also for this process, I skipped the detail, but this time scale is very consistent with the propagation of the transverse acoustic wave in the nanodomain of about 20 nanometer. there is the rough contents of the, I guess the last week at the end has already told. And this is the summary of the result measured, obtained by the 100 femtosecond light path. First thing is that symmetry breaking by the coherent transverse wave in the nanoscale domain, and then there is occurs in the few picoseconds, and then by the acoustic longitudinal the wave can drive the volume change in the 30 picosecond. Okay, so there is a long introduction. So how many minutes I have?
Slightly over 5.
5 plus alpha. Okay.
Plus epsilon.
Okay. Okay. I will be completed within 5 minutes. Okay. So I would like to discuss about the precursory dynamics by using the 6 femtosecond Pomprov experiment. We have a coherent phonon. The Fourier spectrum of this coherent phonon shown here. That we have a clear 3-peak, and this coherent phonon has been already discussed in this paper. And also some controversial problem remains, but they are attributed to the dimer oscillation. And among them, we have a very clear excitation intensity dependence only for this mode. This mode has been assigned to the CR mode. CR mode is shown here as later discussed. Above the threshold, the coherent oscillation decays in the first 1 or 2 periods. In a few periods, the oscillation disappears. Very striking result. And here is the amplitude and the decay time of the oscillation as a function of excitation intensity. And here is the threshold for light-induced phase transition, about 2 millijoule Pascal Hench. And here, the amplitude of the coherent oscillation and also the decay time drastically changed. So there is an indication for the phase transition. And it is easy to imagine that this microscopic coherent oscillation of CR mode is closely related to the macroscopic the structure change. And considering that, I'm not sure the origin of this relation, but considering that the CR, as I told in the introduction part, this CR mode stabilizes the antiferromagnetic electronic state, that the right excitation suddenly the driving force, the reason for this CR distortion is suddenly disappeared by the right radiation. So there is maybe the reason for the very first decay for only this mode. Okay, I have to summarize my result. To elucidate the microscopic mechanism of the macroscopic phase transition, we have measured the very first event depending on the excitation, very wide excitation independence. So the very drastic change in the lifetime of the coherent phonon showed the precursory phenomena for the CR distortion. There is an essence of this right-induced phase transition. So this is the last, the few minutes I have. Okay. Okay, this is a summary. As a conclusion, what I have to say is that the alt-thrust dynamics, maybe toward the 100 attosecond, can clarify the microscopic mechanism of the macroscopic symmetry change. Thank you for your attention.